Well, good afternoon, everyone, and thank you for the introduction. Well, to start, the metals can get to the environment by anthropogenic sources, for example, industrial activity as electroplating, battery and painting manufacturing, and also by mining, fertilizers abuse, and inappropriate waste disposal. Usually, the sediments are in an anoxic state. There is no presence of oxygen. So in this reductive environment, the metals tend to accumulate here. The metals can form insoluble compounds, for example, with sulfides, hydroxides, or can be adsorbed to particles and organic matter. In the water column, there is oxygen present, so in this oxidative environment, the metals usually are in their soluble form. This balance that can happen naturally due to the changes of the conditions in the environment can also be catalyzed by bacteria. The iron II and sulfur oxidizers are the ones involved in the solubilization process of the metals. They are aerobes, heterotrophs, and acidophiles. They grow at low pHs. For example, aciditioacylous ferroxians or thioxians. On the other hand, the iron III and sulfate reducers are the ones involved in the immobilization process of the metals. They are anaerobes, heterotrophs, for example, bacteria of the genre Disulfovibrio or Geobacter. Ferroxians bacteria have an oxidative mechanism. They oxidize iron II to iron III, and this iron III can react with metal sulfides, generating sulfate and releasing the metals. Antioxidants have an acid mechanism. They oxidize sulfur to sulfate, generating acidic conditions in which the metals can also be released. And since my work was focused on uranium, I will also show this particular case. The uranium dioxide is an insoluble compound that can react with iron III or with oxygen in an acidic medium and can form this soluble uranyl ion. In the case of the reducers, they oxidize organic matter, reduce sulfate and generate sulfides, which can generate the insoluble metal sulfides. So this kind of bacteria can be used for metal recovery, and the oxidizers can be used for bioleaching. So briefly, the bioleaching is the process where the metals were attached to a solid matrix and they solubilize and transfer to aqueous solution. This can happen by both the oxidative or the acid mechanism. Next, I will tell you about my site of study. In the southern region of Argentina, there is an uranium enrichment plant. And close to this plant, there is a natural wetland, which in the 90s was contaminated by heavy metals, such as uranium, nickel, tin, and copper. And the metals have accumulated in its sediments. Here, there is a picture of the wetland that actually is not a very wet land because it has a very long and dry season. So the idea of this work was to take samples of the wetland and to develop bioleaching processes in order to release the metals from it. To do that, first we took samples from the bottom and the slope of the wetland and made a physical and chemical characterization of the sediments. We made a quantification of several parameters. We made a granulometric study, sequential extraction of metals, and with this information, we knew the initial conditions of the sediments, their characteristics, and we could develop the best kind of bioleaching. We also noticed that the bottom had high uranium concentrations, up to 100 times than the baseline. So we chose this sample to continue with the experiments. Then we tried to isolate microorganisms involved in the bioleaching process, but we couldn't achieve this because the sediment had a lack of sulfides and reduced iron, which are the substrates that the bacteria need to grow. So instead of that, we used stock strains that we have in a laboratory to continue with experiments. And finally, we developed the bioleaching experiments. First, we made them in a batch condition, and with the obtained results, we developed heaps. In this case, we used shaked flasks with 5 grams of sediment and 100 milliliters of culture media. And we used 2 grams of iron per liter in a soluble form and 5 or 20% of sulfur. And we tested several combinations of additions of these external electron sources. We obtained that the best condition was when both iron and sulfur at its highest amount were added, and we got high metal percentage of metal removal. In the case of uranium, it reached 100%, and for the other metals, it was higher than 90%. But since this kind of treatment is very difficult and expensive to apply on a large scale, big amounts of sediments are treated by heaps. This is why we developed bioleaching in columns. In this case, we used 90 grams of sediment and 100 milliliters of culture media, daily recirculated, and we used the same amounts of iron and sulfur. Here we can see a picture of the columns. They were made from recycled bottles. They had a filter at the bottom, on top of that the sediments, and the sulfur was added on the surface. And samples were taken periodically to measure the metals and parameters of the bacterial growth. In this case, we also saw that the best condition was when both iron and sulfur were added, but we obtained lower yields. This is something that occurs when the scale of the process is increased, but we are working currently on how to improve this. And maybe I have already spoiled you the results, but I wanted to show you briefly how the figures look like. We can see how the pH decreases over time, while the amount of uranium in the leachate increases. And at the bottom, we have parameters of the bacterial growth. We see how the acidity increases and the iron decreases because it's oxidized by the bacteria. The sudden increases in the iron concentrations is because of the addition of new culture media. And we can see in purple how the best condition is obtained when both sulfur and iron are added. So in conclusion, the bioleaching and metal release from the sediments were possible. We managed to develop heaps from the batch condition, and since bioleaching is the technique applied on a large scale, these obtained results are promising for advances in the treatment of contaminated sediments. Thank you.